crois qu'on est tous là, hein, il me semble.
Mais j'attends le signal, en fait. Vous me dites. Si vous voulez qu'on commence, on peut commencer.
Moi, je pense qu'on peut commencer.
Faut y aller, oui, oui.
Alors, on peut y aller formellement, alors. Alors, déjà, bonjour à tous et bienvenue. Donc, on est réunis, en fait, pour la soutenance de thèse de René ZUNIGA, qui a travaillé donc sous la direction, donc en co-tutelle, soutenance d'une thèse en co-tutelle entre l'université en fait catholique de Valparaíso. Donc pour cette université-là, l'encadrant c'était Germán Varas qui est professeur, et on avait une co-tutelle avec donc SUPMECA. Donc, c'est en réalité donc l'université Cergy Paris Université, sous la direction de Jean-Yves Chollet, qui était directeur de thèse, et le co-encadrement en fait, de Stéphane Job. Donc, les membres du jury sont, en fait, le jury est composé de 2 premiers rapporteurs, en fait, qui ont évalué le manuscrit et on nous donnait l'autorisation de cette soutenance, à commencer par Vincent Tournat, qui est directeur de recherche au laboratoire d'acoustique du Mans. Et le deuxième rapporteur au Chili, cette fois-ci, c'est Nicolas Mujica, qui est en fait professeur au département de physique de l'Université du Chili. Le jury est complété en fait d'un premier examinateur, Francisco Melo, qui est professeur à l'Université de Santiago du Chili, au département de physique de l'Université de Santiago du Chili, et de moi-même. Donc, Jean-Christophe Giminard, je suis directeur de recherche au CNRS et je travaille au laboratoire de physique de l'ENS de Lyon. Et mes collègues m'ont désigné comme comme président de ce jury. C'est pour ça que je prenais la parole. Et donc, on va écouter René pour 45 minutes d'exposé. La soutenance se passera en anglais. Je pense que ça sera plus confortable pour le candidat. On pourra poser des questions ensuite. Voilà, donc René, tu as la parole pour 45 minutes.
Merci. Vous m'écoutez?
Parfait, vas-y.
Merci. Okay, good morning, everyone. I'm René ZUNIGA, and PhD students under the Chilean French Collaborative Agreement of Thesis between the Pontificia Universidad Católica del Paraíso, Chile, and the Université de Cergy Paris and SUPMECA Conference. My advisors in this thesis are my university advisor is the Professor Jean-Yves Chollet from SUPMECA, France, and scientifically under the supervision of the Dr. Stéphane Job from SUPMECA and Dr. Germán Varas from Pontificia Universidad Católica de Valparaíso in Chile. Also, we are associated with the LIA and SD Association, and in this stance, this thesis defense is titled Phase Transition in Bible Granular Media. The motivation for this work is the next. This video shows a classical experiment in the study of Bible granular media, search and analyzing a set of vibrate particles between the control parameters. We have, for example, the injection of energy, the particle size, and the number of the particles or the material of the grains, etc. During the last 40 years approximately, this vibrate granular system has been studied from many points of view. However, the role that the container where the system is vibrant has not been studied. So for this thesis, we have this question is, does the geometry of the container have a role in a vibrant granular media? This is a brief preview. We have 2 images where the image below shows or attempt to modify the geometry of the container. We see there is a difference in the structure of this system. So in this work, we're going to describe the dynamic of this in phases. For example, it's we can determine the phases in vibrant granular media, for example, let's say solid phase or fluid phase in this case, and we can control these phases, changing the geometry of the container and respect to the other parameters. How do you modify the behavior? By changing only this parameter and keeping the other constants. And for this work, this background is the fundamental point of view of the phase transition the granular damper, for example, it does the geometry, when we change the geometry, it does more disorder, imply more dissipation in this system. And the relation between phases and waves in a bivertical media. For example, from classical thermodynamics, we know the velocity propagation for a perfect gas, and we can extract this information and apply it on our system. So please listen to me in this presentation. I will display you everything. This is the next online for this presentation. First, we're going to see an introduction with a brief description about granular media, phase transition, topology, and the previous word for the objectives. Next is the experimental setup used with the particle tracking and the analysis to describe our system. Next, we're talking about the results obtained, and this section consists in two parts. The first is about phase transition, and the second is about the dissipative aspects. And finally, the conclusions and perspectives. We start with a classical definition of the granular media, and the granular media is a collection of macroscopic particles, and the particle size interact by contact. The particle size is typically greater than 100 micrometers. For example, between 1 micrometer to 100 micrometers, we have powders, and between 1 nanometer to 1 micrometer, we have colloids. With respect to the particle size, we have a monosphere system and polysphere system. Where the monosphere system, the system tends to arrange itself in a hexagonal structure. For example, for this beautiful image. And for polysphere system, we have, for example, serials. In the granular media, the thermal fluctuations are negligible, unlike the powders when we have van der Waals interaction and humidity effects. And for colloids, we have the thermal fluctuations are not negligible. And it's a highly dissipative system because there is a lot of collision and slices, and there is a lot of dissipation in the system. And it's the second most handled material in the industry, for example, for the pharmaceutical, mining, and food industry. To understand this system is very important because since there is a collective behavior that can be related, for example, with the phase transitions in these systems. For example, we have an static peel of grains, and the behavior is like a solid phase, and we have a fluid phase in this system. Depends on the situation, but for example, we have a sun clock and sun storm, and the behavior is like a fluid phase. Also, there is an analogy for that is the classical description. For example, for water in the phase transition, we have solid, liquid, and gas phase. And to generate a phase transition, we change the temperature and pressure. This is a typical diagram when we have the different phases, the transitions and coexistence of phases depends on the pressure and temperature. But we usually change the temperature for generate a phase transition. And for the phase transition by bivertical media is by the injected energy. Respect to the phase transition, we have a classical description using the free energy and modern classifications. The first order phase transition, there is involved latent here. During this process, the temperature of the system will stay constant as heat as added or loose. The system is a mixed phase regimen, and in which some parts of the system we have complete the transition and the other have not. An example of the first order phase transition is the water, the melting of the ice or the boiling of the water. On the other hand, the second order phase transition is a continuous phase transition where there is an infinite correlation length, a powder law decay of the correlation near critically. And an example for second order is the ferromagnetic to paramagnetic phase transition. This is a transition from order to disorder in the system when the temperature is greater than a critical temperature. With respect to the phase transition in bivertical media, I say it's by the injected energy. And for understand that, we have this simple case is a single bivertical particle where the most important control parameter is the dimensionless acceleration that consists in the acceleration of the display over the gravity acceleration. And this parameter is very important because when gamma is less than 1, the particle cannot detach and continue with the plane. And when gamma is greater than 1, the particle can detach and the particle is pausing. With respect to the interaction, I say the interaction in the ground media is like contact, and we consider the case for two particles is a normal repulsive force that consists in elastic force, depends of the deformation with exponent 3/2, so that is a nonlinear force, and the dissipation depends of is proportional of the deformation rate. And with respect to the dissipation, we have, for example, this example for granular damper, where if we have a container with grains and the container is vibrant, there is collisions and slices in this system, and the energy dissipates very quickly with respect, for example, a solid mass in the same container. Now let's see the phase topology to describe these systems. First, we're going to see the fundamental phases in the nature. We have solid, liquid, gas phase, and if we have ionization, we have plasma, and this is the different transitions. And to generate a phase transition, we change the enthalpy. The enthalpy consists in internal energy, and usually is as a function of the temperature and pressure volume. Also, there is no classical phases, for example, glass, liquid crystal, superfluid, Bose-Einstein condensate, among others. For our case, it's very important to consider a two-dimensional system of particles where the melting is the transition to solid to liquid phase. And for these systems, there is an intermediate phase, is called excited phase. With respect to the excited phase, the melting is made by topological defects, and topological defects are interruption of a regular pattern in the structure. For example, we have point defects with the dimension series when, for example, when we put or remove one particle in the structure, is a point defect. Also, we have a line defects, is a defect with the dimension 1. For example, when we put one column in the system, it's an edge defect. Also, there is the high dimensional defects, for example, planar and bull defect. And the theory to describe this excited phase is the KT-HW theory by Kostelis, Tudles, Halperin, Nelson, and Young theory. And this is very important because it's a Nobel Prize in Physics in the year 2016. To summarize this excited phase, we have this table to compare it for two-dimensional hard disks predicted by this theory, where we have this excited phase. For example, with respect to the positional order, we have a short range, but for both rotational order, we have quasi-long range both rotational order. With respect to the crystal and crystal phase, when we have a long range both rotational order, and for liquid phase, we have a short range. And with respect to the topological defects, we have in the excited phase, we have three dislocations and declinations in pairs. We're talking about this in the next slides. Next, let's see the investigation proposal for this. Let's see the previous work. There is a lot of previous work, but for this instance, we only mention 3 words as a brief evolution of these words. The first is Olafsen and Urbach. There is one of the first words where they show the particle correlation and only short range order as a two-dimensional sphere gas in equilibrium. Also, they showed a second order phase transition diagrams as a function of the parameter, this parameter gamma, and the frequency. Also measured velocity distribution and not Gaussian distribution showing new exponential tails. Next is Claire et al. They reported a second-order phase transition. The transition is made by waves and triggered by a negative compressivity as a van der Waals coexistence in the system. And the most recent research is Castillo et al. They experimentally studied the critical properties of non-equilibrium solid to liquid phase transition. The critical dynamics is characterized by the coupling of the density field and the both orientational order parameter, which measure the degree of the local crystallization. In the last, in these previous words, the role of the container geometry has not been explored. For this, we have then these objectives for this thesis, and you can see we usually the ground phase transition depends on this parameter gamma, and there is a lot of literature about that, different point of view. But in this previous work, the role of the geometry, the container geometry has not been explored. I want to explore in this thesis. For this, we aim to study the phase transition in bipolar media at constant inject energy, change the geometry of the container, and explore the dissipative aspects of bipolar media, change the geometry. For this, let's see the next experimental setup used. This is the sketch for this experimental setup. Is a quasi two-dimensional cell or Herschel cell, and inside we put a random media, and that consists in 550 steel beams with 2 millimeters of diameter. And to change the geometry of the container, we use a 3D prime template. In this image is this, and it's a B-shaped template with the parameter for change the geometry of the container is the angle. It's the same for these places, and the cell is vibrated by vibration exciter, and we record the particles using a fast camera with these specifications. And for each experiment, we control the acceleration and the angle to change the geometry of the container. The next is a typical video in our experiments. We can see we record the particles, and the next step is the particle tracking. To explain that, I'm going to use these steps. The first is a zoom an image where for each particle there is a light spot, and also there is a noise from the background, the external reflection in the cell. But we use a low pass filter to remove the high frequencies, and we conserve these light spots. The next step is the detection, where we have two detections. The first is the peak detection, when we detect by intensity of this image, and this peak detection is a pixelan level. And the next is the centroid detection, where we have a subpixelan level of the resolution. And if we apply this detection, we have this final result, and we can see we can detect all particles in this image. And the next is, for example, if we have the position for each image, I need to estimate the velocities for each particle. For that, we use a tracking algorithm, and for this case, we use the AGL particle tracking algorithm. And for example, we can estimate the velocity field in this system, and we can estimate, for example, we use this information, for example, for estimate the statistics in this system. The next is from the positions. We studied the topology in this system, and let's see the single case, just one particle, is from the particle position. We estimate the Delaunay triangulation and Baron tessellation for each particle, and for with the Delaunay triangulation, we estimate the number of the near neighbors, just when we count the near neighbors for each particle. And for example, for hexagonal plus backing, the number of the near neighbors is 6. The next is the local compaction. It's a two-dimensional quantity where it is defined by the area of the particle over the area of the Baron tessellation. It's a local compaction, and the maximum value in this quantity is for hexagonal plus packing is close to 0.91. And for our analysis, we use the Rose local compaction. It's just the compaction over the compaction for hexagonal plus packing, and the maximum value for this case is 1. And also the local order parameter is using this form. I'm going to explain why I use physics and no order, but the maximum value to characterize the order in this system is, for hexagonal plus packing, is 1. This is for a single case. Now is the final result for all particles in one image. We have the number of the neighbors, local compaction, and order parameter. Now we can see the large number of particles tends to 4 hexagonal lattice when the number of the neighbors is 6 and the local compaction of the parameters is close to 1. At the edges of the central cluster, the topological defects originate in the base, and these defects originate due to the symmetry broken of the B-shaped base. To understand that, I'm going to use this example respect to the symmetry in this system. So we have the image A is for a flat case with an angle, and this is a monosphere system. I say the structure tends to arrange itself in a hexagonal lattice. This is an example in my experiment. And also, when we have this system with an angle of 30 degrees, is when we just cut the lattice and the symmetry is the same. In other words, 0 and 30 degrees are equivalent for all cases. But when the angle is between 0 to 30 degrees, the symmetry is broken, and we can generate disorder, change the geometry of the container. Next is the results. The first part is about phase transition. We start with the static analysis, where I use the number of the neighbors because the pairs of particles with a number of the neighbors is 5, 7 are topological defects. And we can see this in the next plot. This is a scatter with the number of the neighbors, and we can see we can detect these pairs 5, 7. There is a lot of pairs at edges. There is a lot of little points with these topological defects. But when we have an intermediate angle, we can see there is topological defects at the edges also, but in this zone also. To quantify that, we estimate the fraction of the defects. We count these pairs over the total number of particles, and we can see this is in this zone of the dissymmetry, we have more topological defects. So when we change this geometry in the container, we have more topological defects in the system. So next is a dynamic analysis. For that, we estimate the average of the local compaction of the parameter and the number of the neighbors. Figure A is the average of the number of neighbors, and we can see the number of the neighbors in time is constant with a small fluctuations. Respect to the local compaction and other parameters, we use for these examples, I use these parameters to compare the result. And when these curves fluctuate at the driven period around an equilibrium value, we estimate this equilibrium value. It just is an average in time of these curves, and we can see this equilibrium value as a function of the acceleration. And when gamma increases, these quantities decrease monotonically. And also, this is important, the next blocks, each curve is at constant acceleration. And we can see in the topological dissymmetry result more diluted and more disordered structure in this zone. Next is the phase identification. For this, let's see these results. The figure F shows the probability density function of the other parameters for these cases. The curves show a coexistence of two phases in the system, an amorphous phase represented in a distribution centered at 0.5, and a crystalline phase with a distribution centered at 1. This distribution cross at 0.85. Also, in the figure G, you can see the local compaction and other parameters are linearly related. There is a correlation between the local compaction and the other parameter. With above, we estimate to set a threshold to determine the solid phase in our system equal to this crossover with respect to this figure. So we estimate the solid-like particles using this condition when the particle size and when the local compaction and other parameter is greater than or equal 0.85. This is solid-like phase, and when the condition is not satisfied, is fluid phase. And this is a video to illustrate that the blue particles is solid phase and the red particles is fluid phase. And we can see there is an evolution of these colors when the system is vibrant. For that, we estimate the solid fraction. We can see these cases. This is more fluid case because we can see there is not a lot number of the solid particles, and also there is an evolution of that. But the less fluid case, we can see there is a lot number of the solid particles, and also there is an evolution of these particles in time. For that, we estimate the solid fraction. Solid fraction is just the number of the solid particles over the total number of particles. And we can see these curves of the solid fraction as a function of the time. We can see the same behavior. The solid fraction fluctuates at the driven period around an equilibrium value. And this equilibrium value we can estimate from the average of in time. And we can see this solid fraction when gamma increases, the solid fraction decreases monotonically. And also, we have the in terms of the angle, each curve is a constant acceleration, and you can see in the topological dissymmetry result more diluted system at constant acceleration. And this is the same. This is the normal with normal this curve in the figure C. And we can see more dynamic in this case. So there is an effect of the when we change the geometry of the container. Yes, and this relate with the solid fraction. The next result is the statistical analysis. For that, we estimate the relative velocity when we remove the average of this velocity. And also we have the histogram of these, the horizontal and vertical velocities for the same cases. And we can see the distribution, not for a normal distribution. This is the red line. It's a normal distribution fit. And the horizontal distribution is symmetrical, independent of the angle or acceleration, and the vertical distribution is displaced. Now, next, we estimate the temperature. The temperature respect to the horizontal or vertical direction is proportional to the square of its standard deviation of the respective velocity. And we estimate this total, this absolute temperature with this approximation. And we can see the temperature is anisotropy because there is more fluctuations at the vertical direction. And this curve have the same behavior, fluctuate around an equilibrium value. And we estimate this equilibrium value in the figure D. And we can see in this zone of the symmetry, we change the anisotropy in the system. And also we estimate the energy from using this absolute temperature as a function of the angle. Each curve is at constant acceleration, and we can see there is more energy in this dissymmetry zone, and it's related with there is more the fluctuation of the velocity in this dissymmetry zone. The next is to study the statistical moment. We estimate these statistical moments, and for example, for skewness and kurtosis, when these statistical moments is equal to 0, we have a normal distribution or Maxwell-Boltzmann distribution, or we have a perfect gas. We estimate these statistical moments, overall particles and time, and we can see for the second moment, curves are arranged in an increasing order with the accelerations proportional to the granular temperature, and at constant gamma, the second moment increase with the angle, possibility related to more disorder generate following fluctuations. With respect to the skewness and kurtosis, the skewness curves, there is a transition as the acceleration increases, and for kurtosis, the curves collapse in the same place, and it's approach 0 for intermediate angles. And the most important is, in general, we can obtain, when we change the angle and acceleration, we can obtain a distribution close to Maxwell-Boltzmann distribution, because in this zone we are close to 0. Okay, for this, with the above, we build a model using the Maxwell-Boltzmann distribution, or the hypothesis showed before, with the analysis of the statistical moments. The phase transition occurs when a particle is displaced from this its lattice. to means that the particle must have a certain energy greater than a critical energy to move and produce a topological defect. This is this case. From the Maxwell-Boltzmann distribution, we have the following probability density function of the velocities and the cumulative density function is the probability to find a particle with energy between 0 and energy E, respect to this velocity at temperature T. So we have a solid phase have an energy less than this critical energy to generate a topological defect. According to the Maxwell-Boltzmann distribution, the solid fraction corresponds to the cumulative density function of this critical energy. This figure corresponds to the solid fraction from the topology analysis as a function of the temperature or from a statistic analysis. By means of the Kubert fitting, this value of the critical energy is obtained, and we compare it with the energy required to insert or remove a frictional particle inside from a hexagonal lattice, and we found the coefficient mu is 0.212 is reasonable to steel particles. In this case, we only parameter setting is the critical energy. Here we have a good agreement between the experiments and model demonstrate a link between the topology that describe the phase description, the solid fraction, the statistics, and the mechanics, because this is just mechanics, just the energy necessary to move one particle. Here we have this approximation, and also we estimate the orientational correlation function from the other parameter and the correlation length, where we found a second order phase transition with exact phase in the KTHY theory, because in this there is no adjustment of the parameters. So we use these same experimental points for that. And also we found this critical temperature from this critical energy estimate. Okay, in this field trial, we concentrate on study the phase transition of the system. Now we're talking about in the different topic, such as the study of the dissipation. This work was mainly studied using molecular dynamic simulation, and we use the discrete element method. This is the ground media is a nice system to use this method. This method was developed by Peter Allen Kundal in the year 1971. And for our simulation, we use the software Jade. It's an open source software that was developed by the 3SR laboratory in Geneva, France. In this method, it's very important the determination of the interaction forces between particles and the container also. And for example, we have the stiffness with the the interaction. We have a normal direction and tangent direction. And for spherical particles, we have the Hertzian interaction. I say about that. We have elastic force, depends on it's proportional to the deformation with exponent 2/2 and the dissipate force. Now, to study these dissipative aspects, I continue the original idea from is a work from Marwa Masmundi. She was a PhD student supervised by the Dr. Stefan Job. And we consider study these concepts. For example, if we have this sphere container with particles and the particles is vibrated by vibration exciter at this frequency omega. If we measure the force and acceleration, we obtain these curves. This force as a function of the acceleration, and also if the system is vibrate sinusoidally, we have the displacement. And the overall dissipated energy per cycle corresponds to this charged area. And we estimate this dissipation of energy when the acceleration of the impulsive motion is set to the gravity, the particles start to bounce periodically on the bottom of the container. The collisions induce a nonlinear spectrum in both the force and acceleration. In addition to strong attenuation of the vibration, one feature of interest results is characterized by dissipate the energy at the driving frequency. And we estimate this loss factor is the energy dissipated per cycle over to be times the maximum kinetic energy stored during a cycle. And with respect to this force and acceleration, this loss factor depends of this phase between the acceleration and force. Is related to the work of the friction, respect to the friction, and also we estimate the reduced loss factor is just the mass of the grains over the mass of the container. And Marwa et al. Showed this analytical description using the inelastic Boson-Bond model, and they estimate this energy, and we found an analytical approximation for this local order parameter, but sorry, this loss factor. And this is the numerical result in this plot of the question one, and the second is the envelope of this system. As a base of this work, we reproduce the results obtained by Marwa, and these results is the one-dimensional simulations, and zero dimensions, just one particle vibrate. And we have, for example, for one dimensional simulation, we have a granular chain on the vibrating plate, and using J, we can obtain, for example, the position of the particles and the cumulative density dissipate as a function in time. And from for these parameters, we can obtain the reduced loss factor as a function of the acceleration. Each point corresponds one simulation, and I did a lot of simulation to learn this method. We can see for one particle and 20 particles, we have a good approximation with respect to the analytical model developed by Marwa et al. Simulation of one-dimensional chain as a minimal dimension to account for the depth to packing and propagation of wave developed that is a zero-dimension system in elastic positive mode. Our contribution was to see the two-dimensional simulations using the software J. I prepared this system with the same geometry of the container. This is a simulation to prepare that, and I used 1,100 particles with the same radius. To compare it, we have this This video, the first is an experiment, and the second is the simulation. And we can see we have the same behavior in these systems. And also we estimate the particle position and the cumulative density dissipate. And we estimate these results. The figure A is the simulation and B the experiments. Initially, we have a good order of magnitude in the loss factor, and problems appears when the acceleration is greater than 5 times the acceleration of gravity. As an approach, we can see that the loss factor does not depend on the angle. This is not trivial result since the fluctuation dissipation theorem. It says that the fluctuations are related to the dissipation of the system. But by changing the geometry of the container, we should increase the disorder between the particles and increase the fluctuation. That is their dissipation. According to this observation, the dissipation does not depend on the disorder in this system. The problem is not very clear for us why it occurred. For the conclusions and summary, for the image analysis, we can obtain the particle tracking and estimate a local compaction and other parameters at every particle to characterize the topology in the system, and the angle of a bit-shaped boundary can use the change the proposal in order to break the symmetry of the crystal lattice and control the amount of the disorder. We quantify the fluidization of the medium in terms of the solid light or fluid-like particles and the system and the statistical analysis, and we found the second order phase transition with a exact phase. And it's possible to initiate a phase transition and control the fraction of the fluid particles by changing the geometry of the container at constant inject energy. The perspective for this work is the first is wave propagation by the medium. We can see there is the velocity field in the system, and when there is a collision between the container with the grains, we can see it wave propagate vertically. And to study that, for example, we estimate this average using these rows when we put the space in this image, and we estimate this space-time diagram of the local compaction. We can see there is this pattern. There is a slope, and we consider to estimate the velocity propagation, and this velocity is 7.5 meters per second. And also we can estimate the vertical and average of the vertical velocities. Each cube corresponds an average in this row. And for example, if we track these maximums in these points, we can estimate also this velocity propagation, and it's the same order of magnitude using these methods. And also the effect of a soft intruder on the dynamics of bible media. This soft intruder is and this with the same particle size, and we use an elastomer to change and modify the system. And this is a future work in my thesis. The acknowledgements, I say thank you to the commission to listen to my presentation, and my advisors, my family, friends, and also the ANIT, SUBMECA, and the Pontificio Universidad Católica del Paraíso for the support during this thesis. Thank you.